The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. Thanks for joining. We're just going to wait a couple more minutes to get started for a few more attendees that will probably be arriving. So just hang on for a minute or two yet. Okay, hello everyone. We're going to get started now. So thanks everyone for joining us today. And we're here today to launch a new report of the IEA, Material Efficiency in Clean Energy Transitions. And I'm Tiffany Vass from the IEA's industry team, and I'm here with my colleagues Thibaut Abergel from the buildings team and Jacob Teter from the transport team, and we'll be presenting the report today. We'll first go over an overview of the report and then get into more details about the buildings and transport portions of the analysis. And please feel free to send in any questions you might have throughout, just through the online webinar system, and we'll try to save some time at the end to answer as many of those questions as possible. All right, so first, just a bit of background on the IEA. So the International Energy Agency is an autonomous organization that works around the world to support accelerated clean energy transition with unparalleled data, rigorous analysis, and real-world solutions. The IEA's mission today revolves around three core priorities: economic development, which means supporting free markets to foster economic growth and eliminating energy poverty. Second, environmental awareness, analyzing policy options to offset the impact of energy production and use on the environment, especially for tackling climate change and air pollution. And third, engagement worldwide, working closely with partner countries, especially major emerging economies, to find solutions to shared energy and environmental concerns. And so the IEA global family includes 30 member countries, which are shown here. And we also have a number of association countries and partner countries, which we're working with closely in this area. And now we see the countries around the globe that we are working with to collect energy data and information. And so now we'll go right into the materials efficiency report. So the motivation behind the report, as the name suggests, is to look at the role of material demand and material efficiency in achieving decarbonization objectives. And so in this report, we focus on three key energy and emissions intensive materials, being cement, steel, and aluminum. And we also look at plastics demand from the vehicle side. Now, these materials are essential to our everyday lives as they make up the buildings that we live and work in, the vehicles we move around in, and many other important products and infrastructures that are a part of our lives and economies. Now, since these materials are so closely connected to our daily lives and business activities, growth in material demand is closely connected with both growth in population as well as economic development. So we can see here that over the past decades, global demand for key materials has grown considerably. Since 1971, global demand for steel has increased by 3 times, cement by nearly 7 times, primary aluminum by nearly 6 times, plastics by over 10 times. And this growth in material demand has coincided with both population and GDP growth. Over that same period of time, population doubled and GDP grew by nearly 5-fold. So it's evident then that materials provide important benefits to us, but they also have implications for sustainability. And 2 of those key implications are their role in energy consumption and on CO2 emissions related to the production of these materials. And so as we can see, over the past 25 years, as material demand has grown, energy consumption and also CO2 emissions have grown by nearly 1.5 times. And as a result, in 2017, industry accounted for nearly 40% of total final energy consumption and nearly a quarter of direct CO2 emissions. Now, if these historical material demand trends continue into the future, we'll likely see an increase in material demand in the coming decades, and this is because we expect to see population and GDP continue to grow as well. By 2060, we would expect to see a 30% increase in steel demand relative to current levels, 10% growth for cement, and 75% for aluminum. And this material demand will pose some challenges for sustainability, including an increase of approximately 15% in industrial CO2 emissions compared to current levels. And so this is if we aren't taking considerable action relative to historical and current pathways. So if we're to achieve as a global economy significant decarbonization of energy systems, it's important that we take a look at material production. Now, emissions reductions and material production can be achieved through adopting process technology changes. This includes energy efficiency measures, fuel switching, shifting to innovative production routes, and adopting carbon capture and storage. However, an often overlooked mitigation lever for industry is material efficiency. This involves using material more efficiently to reduce overall material demand, as well as other aspects of the way that we use materials that can help to reduce emissions. And while, of course, material efficiency does not in any way eliminate the need for strong efforts to reduce the emissions intensity of material production, it can contribute to emissions reduction by reducing the deployment needs for low-carbon industrial process technologies to achieve the same CO2 emissions outcome, and it can also facilitate emissions reduction in other sectors through more material-efficient value chains. So what exactly is material efficiency? Well, here we're referring to broadly 3 different aspects. First and foremost, we're talking about measures that can put a downward pressure on material demand. However, we're also talking about measures that would enable lower emission material production routes. This includes, for example, increasing metals recycling to enable a higher uptake of lower emission secondary production routes, and it can also include switching to materials that have lower production emissions. Thirdly, we're talking about ways of using materials that can facilitate emission reductions in other sectors. So in some cases, this may lead to an increase in demand for some materials, but this increase would be outweighed by CO2 emission benefits at other stages in the value chain. And so a wide variety of material efficiency strategies can be applied across different stages of the value chain. In the design stage, lightweighting and optimization can enable using fewer materials to provide the same service, and also ensuring that we design products and buildings for long life and reuse can help to reduce material demand at other stages in the life cycle. In the fabrication stage, waste and overuse of materials can be reduced during the materials manufacturing stages, when constructing buildings, and also when manufacturing products. In the use stage, encouraging repair and refurbishment can help to extend broad building and product lifetimes, and this can displace the need for new materials to be produced. Also, using products more intensively can similarly reduce the number of products that need to be produced in the first place. Finally, at the end of life, reusing materials can reduce the need to manufacture new materials. And when reuse isn't possible, recycling can help to enable lower emission secondary production routes. In many cases, these various different strategies interact with each other, in some cases leading to synergies with each other, and in some cases putting some degree of limitation on the other strategies. And so to explore material efficiency in more detail, our analysis looked at 3 different scenarios. So first we have the reference technology scenario, and this scenario, which we also refer to as the RTS here on the slide, it accounts for current country commitments to limit emissions, including nationally determined contributions pledged under the Paris Agreement. In this way, it already represents a major shift from historical business as usual approaches that have no material or no significant climate policy response. However, in this scenario, global emissions increase by 8% by 2060 above current levels, and this pathway is clearly far from sufficient to achieve the objectives of the Paris Agreement. In the industry sector in particular, emissions increase by 15%. Our second scenario is the clean technology scenario, or CTS, which is our central decarbonization scenario in this analysis. It lays out a pathway in which CO2 emissions related to the overall energy sector are reduced by around 3/4 from today's level by 2060. And it represents a highly ambitious transformation of the global energy sector and is in line with pathways projecting a median temperature rise in 2100 of around 1.7 to 1.8 degrees Celsius. On the industry side, emissions declined by 45%. And as you can see in this chart, material efficiency makes a considerable contribution to the emissions reduction in this scenario. However, the clean technology scenario is certain to be a highly ambitious pathway for industry from a technology perspective. And for this reason, we also developed the material efficiency variant. It's a variant on the CTS, or clean technology scenario, that achieves the same emission reductions in industry as the clean technology scenario. However, it pushes material efficiency efforts further to reduce some of the need to deploy low carbon industrial process technologies. And so the strategies pushed considerably further in the variant are those that are more challenging to adopt from the perspective of requiring greater stakeholder coordination, regulatory efforts, value chain integration, or behavioral change. And while we consider it to be highly ambitious on material efficiency, we do consider it to be within real-world technical, political, and behavioral constraints. And so now we'll go into some of the results of the scenario. So as you can see from these graphs, material demand varies considerably across the 3 scenarios. In the reference technology scenario, demand by 2060 grows by approximately 30% for steel, 10% for cement, and 75% for aluminum relative to current levels. In the clean technology scenario, we see a considerable diversion from the materials demand trends in the reference technology scenario. In 2060, in the CTS, demand is 24% lower for steel, 15% lower for cement, and 17% lower for aluminum relative to the reference technology scenario. However, considerable potential exists to push material efficiency beyond the clean technology scenario. In the material efficiency variant, we see that demand is reduced by 16% for steel by 2060 and 9% for cement relative to the clean technology scenario. Aluminum, on the other hand, sees a small increase by 5% by 2060, and that's because of vehicle lightweighting outweighs some of the other strategies that are putting a downward pressure on demand. Now, these next slides go into a bit more detail on the different factors that are affecting material demand for these 3 key materials. And so this graph shows the change in material demand between the 3 scenarios. Those are the 3 main bars in the graph, and then we can see the different steps in the waterfall that lead to the change in material demand. So this, focusing on steel, we can see that in moving from the reference technology scenario to the clean technology scenario, one of the key strategies leading to changes is improvement in product manufacturing yields. And this includes reducing really losses in producing things like cars in the manufacturing plants, or perhaps in buildings, creating the materials to go into buildings. We can also see that building lifetime extension leads to considerable reductions in steel demand. And so in this scenario, we have major investments in energy efficiency retrofits, which lead to longer building lifetimes. And these buildings in the reference technology scenario may have been demolished and rebuilt before they ended their useful life, and so extending their lifetimes helps to reduce material demand. Now, in the material efficiency variant, the largest additional savings in steel demand occur from vehicle lightweighting. And we also see significant contributions coming from improved building design and construction, as well as from reusing steel. Now, looking at cement, we can see that in the clean technology scenario, almost all of the reductions in cement demand come from building lifetime extension. And this is again due to the same theory as with steel, that as we're extending building lifetimes through retrofits and repurposing, in concurrence with energy retrofits, we need to build less buildings and therefore see a reduced demand of material. Now, in the material efficiency variant, improvements in building design and construction are improved considerably more. And because of that, that's one of the biggest factors contributing to reductions in the material efficiency variant. And these strategies include aspects such as reducing concrete over engineering, improving structural optimization, promoting concrete steel composite construction, reducing cement content in concrete, and also reducing on-site construction waste. Now for aluminum, we have a bit of a different story as we see both upward and downward pressures on material demand. In the clean technology scenario, a considerable downward pressure on aluminum demand occurs because of improved aluminum semi-manufacturing yields and also improved product manufacturing yields. However, vehicle lightweighting puts a substantial upward pressure on aluminum demand as manufacturers are substituting aluminum for steel to meet fuel efficiency objectives. The net result is a decline, however, in aluminum demand from the reference technology scenario to the clean technology scenario. Conversely, in the material efficiency variant, additional vehicle lightweighting has the largest effect and results in an overall net increase in aluminum demand relative to the clean technology scenario. However, a large proportion of this increase from lightweighting is in fact offset by reductions from aluminum reuse. So what are the implications of these changes in material demand? In the clean technology scenario, material efficiency contributes directly to emissions reductions. It accounts for approximately 30% of the combined emissions reductions in 2060 for steel, cement, and aluminum from the reference technology scenario. In the material efficiency variant, however, there's a bit of a different story, and this is because we maintain the same carbon budget as the clean technology scenario. And so the material efficiency does not necessarily lead to additional emission reductions, but rather enables somewhat lower deployment of low carbon industrial process technologies. As a result, the emissions intensity for cement and steel increase by 7% and 4% respectively in 2060. For aluminum, on the other hand, since demand for the material is increasing, the CO2 intensity of production must decrease somewhat by 9% in 2060 in order to still remain within the same carbon budget. This somewhat increased technological effort in the aluminum sector, however, reduces deployment needs for other mitigation options in the transport sector, given that the higher aluminum demand is caused by vehicle lightweighting to reduce transport use phase emissions. And so due to the lower need to deploy low carbon process technologies in steel and cement, which is greatly outweighed by the increased effort in aluminum, we see an overall reduction in technology and process technology investment across these three materials. And so the combined net cumulative process technology investment for these three materials is 4% lower in the material efficiency variant compared to the clean technology scenario. And to provide an example of what this may look like, in the cement sector, the cumulative captured and stored CO2 emissions are 45% lower in the material efficiency variant compared to the clean technology scenario. Now, this shows the impact of if we had looked at the material efficiency variant slightly different. So if we had applied this clean technology scenario emissions intensity to the material efficiency variant level of material demand, we would have seen a reduction in emissions relative to the clean technology scenario. And so for these three materials combined, we would see a reduction in emissions of 7% in 2060 relative to the clean technology scenario. And so while these are two different ways of looking at the impacts of material efficiency, in the real world, applying material efficiency would likely result in a combination of reducing the deployment needs for low carbon industrial process technologies, as well as actual emission reductions rather than one or the other alone. And so that concludes the initial overview. I'm now going to pass it on to Thibaut to go into more details about the buildings results.
Thank you, Tiffany. So why the building sector? 11%. The manufacturing and use of materials for buildings construction and renovation represented 11% of global overall energy and process-related CO2 emissions. This is what we call embodied carbon, the emissions embodied in building structure. 11% of global energy-related emissions, that means that the embodied carbon of the building sector is greater than the CO2 emissions of the European Union. Among those, more than half stem from steel and cement. Aluminum, glass, insulation, and plastics are secondary contributors. So steel and cement take the lion's share of buildings' embodied carbon, and alone they accounted for around 1.8 gigatons of carbon dioxide in 2017. How much does that green share represent here? Approximately 15% of total buildings-related emissions. We have developed a strategy to reduce emissions related to buildings operations. The emissions from coal, oil, gas, and indirectly electricity and commercial heat will fall below 1.8 gigatons in 2060 in the clean technology scenario. Wait, 1.8 gigatons? That's exactly today's emissions from cement and steel used in buildings. So those are as much as our allowed emissions in 2060 for the entire building sector. Therefore, material efficiency strategies and other efforts to reduce the carbon footprint of materials, such as less carbon-intensive industrial processes, are an important lever to reduce buildings-related emissions. Now, how to address emissions from buildings construction and renovation? As part of this analysis, we have taken a step back to understand where, why, and how much building materials are being used. The building sector consumes today 500 million tons of steel and around 2,000 megatons of cement. So that's twice as much as at the beginning of the 21st century. That growth is driven by different factors. First, we have floor area, which doubled since 1990. Second, building framing, for example, with the share of reinforced concrete frames increasing 15% points since 1990. And third would be building construction patterns, as we see more and more high-rise buildings in the streets, for example. In terms of geographical distribution, we can see that China accounted for approximately half of total material demand growth since 2000. But since 2015, we're seeing a new trend emerging. While the Chinese material demand is leveling off, emerging economies such as India, Southeast Asian countries, or Brazil have seen material demand growth increasing, which makes it all the more relevant to understand typical construction rates and framing in these regions. With lower construction and demolition rates, advanced economies have lower demand in relative terms. However, the CTS involves a doubling of renovation rates to reduce heating and cooling needs, and deep energy retrofits also lead to material consumption, primarily insulation materials, of course, but also steel and cement. How to reduce steel and cement demand for buildings, construction, and renovation? As Tiffany mentioned, opportunities for reducing material use per square meter of new build floor space spread throughout the building's life cycle. One is improving design and specification. This includes structural optimization, for example, tailoring building components to their specific function and reducing overestimation. We also have the possibility to mix different materials, and that is called composite framing. It enables to take advantage of complementary physical properties of different materials. Second would be the optimization of material properties, including, for example, using high-strength steel or reducing cement content in concrete, that is using less cement to achieve the same physical properties for the concrete. After optimizing design and material properties, let's move on to promoting best construction practices, for instance, to reduce material waste, ensure buildings are built to their specifications, for example. An alternative construction technique would be precasting and prefabrication that can help optimize the three strategies I just mentioned through the manufacturing of building elements off-site. It is also possible to use buildings for longer time frames, for example, through repurposing of a building during the use phase. And this is especially true for commercial buildings, as many of them are demolished much sooner than their possible lifetimes. And finally, handling the end of life of buildings elements through material reuse and recycling. What is the result on cement and steel demand. In the building sector, material demand in the reference technology scenario increases to over 30% by 2060 over current levels. This is because rapid construction rates in urban areas, coupled with limited efforts to put in place material efficiency strategies, push demand higher up. In this scenario, which includes current and planned policies, steel and cement manufacturing for buildings construction and renovation would still be responsible for an average of 2.3 gigatons of CO2 annually to 2060. And this is just talking about steel and cement. However, in the clean technology scenario, with widespread adoption of building codes and standards, demolition rates shrink considerably, especially in emerging economies and advanced economies. They also implement large-scale energy retrofit programs, which leads to buildings being used for a longer time. And as a result, steel and cement demands are reduced by 1/4 in 2060 relative to the reference technology scenario. And pursuing material efficiency strategies to their practical limits in the material efficiency variant, the MEF, will reduce steel by an additional 15% and cement by an additional 17% in 2060. Finally, let's look at how material efficiency strategies in buildings contribute to carbon abatement. In the clean technology scenario, material demand reductions lower CO2 emissions from buildings, steel and cement use by 10 gigatons cumulatively from 2017 to 2060. In the material efficiency variant, the cumulative CO2 abatement jumps to 15 gigatons of CO2, so 5 gigatons more. And here is why it's interesting. First, of course, because we are achieving greater emissions reduction, 5 gigatons, that's not insignificant at all. But second, because the additional material efficiency reductions in the material efficiency variant reduce some of the deployment for low carbon technologies on the industry side to produce cement and steel with emitting less carbon. Those avoided investments would have been costly, especially when we're talking about carbon capture and storage. So we save money on the industry side. And third, we also save money in other sectors because the emissions reduction from material efficiency strategies in buildings will alleviate the constraints on other sectors by 5 gigatons. This reduces the need for investments in low carbon technologies elsewhere. The contribution of material efficiency strategies is greater for cement, as you can see here. Actually, out of the 10 plus 5 gigatons abated, roughly 3/4 come from cement. This is mostly because industrial decarbonization alternatives are more limited for cement than for steel. Given renovation rates assumed in our low carbon scenarios, lifetime extension has by far the largest impact, you can see it in green, on material demand. So my conclusion would be that material efficiency strategies in buildings reduce global emissions by 15 gigatons cumulatively to 2060, and that this could be achieved cost effectively given that it alleviates pressures on other sectors. Now we'll move to vehicles with Jacob, my colleague.
Thanks, Thibaut. Just as you saw in the building sector, the growth in the demand, particularly for steel, but also aluminum, has been quite high, especially over the past decade or so. The global steel demand for road vehicles has more than doubled since 1990, over a time when the global car stock and annual sales just about tripled. Road vehicles constitute a major demand sector for materials. Most automotive bodies and nearly all frames are currently made primarily of steel. Other key materials that we considered, especially, include aluminum and plastics. So passenger duty vehicles, or cars, put more simply, currently account for about 7% of global demand for steel and 12% of global demand for aluminum, while commercial fleets, buses, and trucks account for about 4% of steel and 10% of aluminum demand. As you can see, just as in the case with buildings, most of the recent growth in demand for steel and aluminum shown here was from the Chinese vehicle market. As society shifts towards low carbon transport systems, it will be more important to consider the contribution of materials to transport sector emissions. So currently, fuel-related emissions, or the operations of vehicles, account for about 85% of life cycle energy and emissions, and that's excluding emissions from the building and maintenance of roads and parking infrastructure. And that's the case for conventional internal combustion engine, ICE, cars and trucks running on gasoline or diesel. These fuel-related emissions include operational tailpipe and fuel production emissions. So we're looking here at a well-to-wheels perspective. The remaining share of emissions, less than 15%, are incurred by the industrial activities along the supply chain that mine, form, refine, and shape the materials that become cars and trucks. As we transition from internal combustion engines to alternative fuel vehicles, such as battery electric vehicles, running by mid-century on low-emission electricity, the emissions from material production will make up an increasingly larger proportion of the vehicle life cycle emissions. Efforts to lightweight vehicles to achieve fuel economy savings also have implications for vehicle production emissions. So it's important, and it will become increasingly important to take a life cycle approach, let alone a well-to-wheel approach, to assess vehicle emissions both in the vehicle production cycle and in the operations phase to enable the most efficient use of materials in terms of value chain emissions reduction. Just as in the building sector, we assess the material efficiency strategies across the vehicle value chain. We took what can properly be called a life cycle approach. The strategies to achieve material efficiency in the vehicle value chain include lightweighting, which can be pursued through a combination of reducing the weight of components within the same material, for instance, going from steel to high-strength steel to advanced high-strength steel, substituting with other lighter materials, such as aluminum, thermoplastics, and composites. Another strategy is to improve manufacturing yields. Currently, the amounts of steel and aluminum, considerable amounts of steel and aluminum are being lost during the manufacturing of vehicles, with typically about 70 to 80% of steel and 80 to 85% of aluminum entering the manufacturing plant, ending up as part of the vehicle. These are some of the lowest yield losses among end-use applications. The losses occur in part because the quickest and most effective manufacturing methods are used. Giving a priority to material use reduction could improve these yields. Another strategy that we considered is reducing the total number of vehicles in the stock or sold through strategies such as modal shift and reducing the length and number of discretionary trips, so avoiding unnecessary travel. Over the past 4 years, we've improved our capacity to use the modeling tools here at the IEA, the mobility model, to estimate the impacts of policy measures, things like investments in public transit, including rail, city-level travel demand management measures and pricing, but above all, vehicle and fuel taxation in the midterm to shifting increasingly to road pricing to reduce total PKM, so total passenger kilometers on motorized vehicles. Finally, the last strategy that we considered was end-of-life reuse and recycling, and recycling being more relevant for the current vehicle value chain. As for results, this slide shows that for passenger light-duty vehicles, in the reference technology scenario, a combination of increasing stocks and lightweighting leads to a demand for steel that by 2060 is approximately 20% higher than it currently is. For aluminum, the growth is fourfold, and for plastic and composites, the material demand for vehicles doubles. So the long-term potential for using both advanced high-strength steel and material substitution is quite high. The PLDV, the car fleet, goes from about 1.2 billion currently to 2.4 billion vehicles by 2060 in the reference technology scenario. So it's doubling. And despite that, you see only the 20% growth in steel. Note that in the midterm, represented here by 2045, steel demand in the RTS increases and thereafter peaks. In the clean technology scenario, a combination of reduced vehicle sales, rather than doubling by 2060, the vehicle fleet grows to 2.1 billion, so about a 75 to 80% increase. A combination of that and more aggressive lightweighting, improved manufacturing yields, and increased reuse results in a considerable reduction in demand for steel, 50% lower than in the reference technology scenario in 2060. A moderate reduction in the demand for aluminum, 7% lower in 2060, and a 10% reduction in demand for plastics and composites. The greater push for lightweighting in the material efficiency variant results in a further decline in the demand for steel by an additional 3/4 in 2060 relative to the clean technology scenario, and an increase, because this is the material that's being shifted to, in aluminum, 1/4 in 2060 relative to the clean technology scenario, and also an increase in the plastics and composites demand by 1/3. The material use trends for commercial light-duty and heavy-duty vehicles are similar to those as for cars. Lightweighting is the primary material efficiency strategy that's pushed further in the material efficiency variant, and it results in substantial value chain emissions savings for road vehicles. For cars, lightweighting contributes approximately 10% of the global 2060 total vehicle use phase emissions reductions in the clean technology scenario over the reference technology scenario, which is a substantial portion in the context of many other strategies, such as modal shift and fuel shifting, that are also being pursued in the sector. For commercial light-duty vehicles and heavy-duty vehicles, trucks and buses, lightweighting contributes 3% of the use phase reduction in emissions. Pushing lightweighting further to its realistic limits leads to additional use phase emissions reductions in the material efficiency variant, equivalent to an additional 20% of clean technology scenario car vehicle use phase emissions in 2060. While the materials required for this additional lightweighting lead to a moderate increase in emissions for car vehicle material production relative to the clean technology scenario, this is greatly outweighed by the savings in the vehicle use phase. In the material efficiency variant, lightweighting results in a net decrease in car vehicle value chain CO2 emissions of 17% in 2060 compared to the clean technology scenario. Here again, in buses and trucks, the CO2 emissions implications follow similar trends, with a net additional emission savings of 9% in 2060 in that value chain. The absolute CO2 emission savings in 2060 is about 25% lower than in 2030 in the material efficiency variant, despite more aggressive lightweighting. The reason being that a considerable portion of cars have shifted to low emission fuels, namely electrified, resulting in lower savings potential from lightweighting. For commercial vehicles, buses and trucks, the net absolute emission savings increased to 2060, as a large portion of these vehicles, particularly trucks, are still running on fossil fuels. While the net change in emissions for battery electric vehicles depends on the carbon intensity of the electricity grid used to power the vehicle, together with many other factors, in some cases, pushing battery electric vehicle lightweighting may result in a net increase in value chain emissions. This does not necessarily mean that lightweighting should not be pursued in battery electric vehicles, particularly in early periods when the battery costs are still high. Lightweighting could enable larger ranges or lower battery costs, thus facilitating greater uptake of battery electric vehicles. But in the latter periods, the pressure on increasingly scarce or expensive materials used in the batteries may be reduced because lighter vehicles can achieve the same performance, including range, with lighter batteries. So the point of this slide being that the life cycle emission reductions for internal combustion engines, even by 2060, are unambiguous, while just from an emissions perspective, the gains, the benefits are less clear.
All right, thanks, Jacob and Thibaut. We'll now conclude with an overview of some key policy and action priorities related to material efficiency. So as we've seen, economic development has historically relied on increasing material demand, which has led to growing energy consumption and CO2 emissions from material production. Applying material efficiency strategies throughout value chains can help to decouple these trends. And so material efficiencies can help to meeting decarbonization goals by allowing more moderate deployment needs for low-carbon industrial process technologies to achieve the same decarbonization outcomes, and it can also help to achieve emissions reductions in other sectors. So how can we get there? Well, there's various challenges that we'll need to overcome to better promote effective use of materials. Without any sort of incentive or requirement to pursue material efficiency or any explicit demand from consumers, designers and manufacturers or construction companies might be unaware of the possible benefits of material efficiency, or they might choose not to pursue material efficiency due to real and perceived risks, financial costs, or time constraints. Also, fragmented supply chains can present challenges, as well as a regulatory environment that might in some ways restrict pursuit of material efficiency. So we have listed here what we consider to be some key policy and action priorities for stakeholders to help promote material efficiency. And it would require effort from governments, industry, the research community, as well as society to help to overcome some of these barriers to material efficiency going forward. And so one important effort will be to increase data collection and robust life cycle assessment, which can help us to better understand the trade-offs in material inputs and emissions across value chains. It also can help us to understand best practices and also to develop benchmarks, which will be a precursor to regulation. Our analysis also found the importance of considering life cycle impacts in the design stage in particular, since the design can have a considerable impact on the overall life cycle emissions of a product or building. And this can be facilitated by expanding the scope of emissions regulations to cover the full life cycle of products as opposed to only the use stage. It also will be important to continue increasing end-of-life repurposing, reuse, and recycling. Durability and long lifetime should be prioritized in cases where doing so will not lock in considerably higher use phase emissions. Greater uptake of reuse and recycling are also important, and these can be facilitated by better integration of supply chains, perhaps mandating a proportion of reused materials in certain products, and expanding the coverage of recycling requirements. Other adjustments to regulatory frameworks may also be important to better promote material efficiency. As one example, moving from prescriptive to performance-based design standards would facilitate more efficient use of materials. Other government policies may also help, such as carbon pricing and green certification programs. On the business side, adopting new business models and practices can be helpful to promote material efficiency. If businesses plan, monitor, and report material efficiency, this can help to increase a culture of material efficiency among employees and workers. Also, innovative business models can help, such as those that promote the sharing economy and digitalization. Training, capacity building, and sharing of best practices among designers, engineers, construction workers, and other stakeholders can be helpful. As well, finally, on the consumer side, the public can help to direct demand towards products that are designed and fabricated with material efficiency in mind, and they can also make material efficient choices at product and building end of life. And so that concludes the presentation portion of the webinar, and we're going to now take a look at some of the questions. Before we do that, I just wanted to thank everyone for joining us, and also thank you to everyone on the line who contributed in some way or another to this report through your comments or information you were provided. We really appreciate that. And for anyone who wants more information on the report, it's now available online, so please feel free to take a look and let us know afterwards if you have follow-up questions.
Okay, so we have some questions about the building sector. The first one is the clarification point about cement production. So Tiffany presented that total cement production is around 4,000 megatons of cement. And in the building section, we've seen that buildings consume actually 2,000 megatons. I would say that this is because there are infrastructures that also consume cement, for example. And especially, for example, in China. So the most relevant infrastructures could be, for example, elevated rail for high-speed rail. And we've noticed that in China, due to the recent work that our transport colleagues did on rail, that China has built 40,000 kilometers of rail tracks, I think, for high-speed rail, which is more than the current established network for high-speed rail in the world. So this has contributed to considerably increased cement consumption for infrastructures, and that's why buildings consume around half of total cement production. Another question in the building sector was about lifetimes. So what do I mean when I say longer lifetime? And then what's the reference lifetime of buildings that are assumed in our modeling analysis? So when we talk about extending building lifetime, it can be through, for example, renovations. Depending on the level of the renovation, it could extend the lifetime from a couple of years to a doubling of the lifetime in case it's a really deep energy renovation for buildings that would have been torn down otherwise. In terms of the reference lifetime of buildings, it really depends on where we are on the planet, which building codes are in place, and also what type of building we are building. For example, the commercial buildings typically last a bit less than residential buildings. We're talking about 30 years to 50 years maybe. For residential buildings, the range of lifetimes is really higher. It can go really from 30 to 50 years, such as commercial buildings in some emerging economies without codes in place. But it can go generally up to 70 or 80 years on average for advanced economies. And in some particular cities, such as Paris, where the IEA is located, you have some historical buildings that can last for over 100 years or even above 150 years. So it really depends on the geography, I would say, and the regulation context.
Okay, so we have a question related to steel production, and the question asks that there was a graph showing that steel production can be made more efficient, lower energy, and with less emissions. And the question is whether steel production is already quite efficient and how it can be improved. And so while this wasn't one of the key focuses of this particular analysis to look at reductions in steel production emissions, there are many different levers that we can take to reduce steel emissions. Currently, the main production route in steel is through the blast furnace coke oven route, and there's potential to make that process in itself more efficient. On the energy efficiency side, there's technologies such as, just as one example, top gas recovery, which can reduce the thermal requirements of that process. There's also potential to move to other production routes, such as direct reduced iron or electric arc furnaces, which require less energy and also have less emissions. There's also more innovative technologies that can be used, such as carbon capture and storage and use of hydrogen in steel production. So there is considerable potential to reduce the emissions intensity of steel. And this would be an opportunity just to let you know that our industry team is just starting up work on, or has been looking at for a while, but is now intensifying work on an iron and steel roadmap that if you're interested more in that, feel free to send me an email and we can keep you posted on that as well.
So there's a question also about the assumptions behind the life cycle savings from lightweighting in automotive applications, and whether the assumptions behind the life cycle savings might not be too optimistic. And in reply to that question, what I can say is that we used material substitution ratios and informed our estimates of the potential for lightweighting. We consulted the most recent literature, and we also submitted our first estimates of results and assumptions for expert feedback from a number of stakeholders. What I can also say is that despite the fact that in the past you see that lightweighting has not necessarily, the benefits of lightweighting have not necessarily all accrued to fuel economy improvements. Quite the contrary, many of them have gone to improving performance or other aspects of such as acceleration and vehicle performance. The assumptions on the policy scenario, the policy environment in which these scenarios take place, could be rightly construed as fairly optimistic. So as Tiffany laid out at the beginning, The reference technology scenario assumes that the nationally determined contributions are met. This would require a high level of ambition on, in particular, fuel economy standards. And we made our best efforts in consultation with academic and industry partners to estimate the contribution of that lightweighting could plausibly make benchmarking the years 2030 and 2060 to achieving these fuel economy standards. Nevertheless, we didn't get into a full-blown analysis of kind of the costs of different strategies of achieving fuel economy standards, and at some level, the auto OEMs themselves are the ones who have the greatest visibility on those kind of elements. And so I would welcome further input. Once you have the chance to look at the results in the study and the assumptions behind them, for further critical input on those assumptions would be more than welcome.
So we have a question here. I'm going to read this one directly. I think that'll be simplest. It says, you said regulations should include life cycle. However, have you considered that regulations address the wrong legal entities doing so? For example, the automotive producer has no way to change the CO2 footprint of the electricity grid. However, that one is decisive on the question of whether battery electric vehicles are preferable. So on this one, I would note that ideally, from a regulatory perspective, we'd be seeing regulations across the economy as opposed to a regulation alone targeting the vehicle sector. We would ideally be seeing regulations or some sort of policy that either is an economy-wide policy, such as carbon pricing, or regulations targeting each of the different sectors. So at the same time as we're perhaps switching to battery electric vehicles, we're also seeing a decarbonization of the grid. And on the manufacturing side, if we were going to a life cycle regulation, there could be some sort of, I guess, demand pull if we had vehicle manufacturers who are looking to have more or lower intensity vehicles productions. Perhaps they could make demand for lower emission materials, lower emission electricity that feeds into the production of those materials. So that could be another way to help drive it.
And in the interim, when we still haven't gotten to a world where something like CO2 pricing, whether explicit or implicit, is something that's politically palatable, it seems that at the very least, policymakers should be cognizant of and evaluating the impacts of the policies in place, whether they be fuel economy standards or some kind of pricing policies, so that they are on guard to account for potential unintended consequences and take them into account in their policy making. Your point is very well taken, that the regulated entity doesn't always, in most cases, in fact, doesn't have full control over the entire value chain. In almost no cases do they. But at the very least, policymakers should be using the best data available to try to evaluate the potential effects of policies that they're considering. So there's also a question on whether the clean technology scenario is in line with the below 2DS, which was one of the three scenarios presented in the Energy Technology Perspectives 2017 publication. Certain assumptions were very closely aligned with the 2DS, but other, I think, more detailed assumptions were not. As Tiffany said, though, the carbon, expected climate sensitivity was between 1.7 and 1.8 degrees Celsius, which is more or less in line with the B2DS energy systems carbon budget. So you're right that they are broadly aligned. The question of our consideration of these scenarios with the 1.5 objectives, our understanding is that the Paris language targeted not exceeding warming well below 2 degrees. So while there was some kind of language surrounding the ambition to eventually target 1.5, it's still a fairly ambitious target, and it's not what we modeled here in this exercise.
Okay, so I think that concludes the time that we have today for the webinar. So once again, thank you all for joining us, and please do feel free to follow up with any additional questions or comments that you might have, and continue to engage with us on any other related topics. We'd be happy to continue working with you all. And yeah, have a great rest of your day and also a wonderful weekend.